Hi, I'm Ding, and today I'm going to talk about our work, Runtime Protocol Refinement Checking for Distributed Protocol Implementations. So nowadays, distributed protocols are typically accompanied by written or formal proofs. However, even if the protocol itself has been verified, bugs can still arise when programmers translate it to concrete code implementations. The reasons for this can vary. Perhaps the programmers did not fully understand the protocol, or they may have made modifications to the protocol for better performance. So we investigated some distributed systems used in production, including Zookeeper, etcd, and Redis Raft, and found that they all have bugs when implementing distributed protocols. This will result in data inconsistencies and stale reads, which would cause serious issues in real-world applications. So currently, there are many existing works aiming to ensure the correctness of distributed protocol implementations. So the first category of the work focuses on generating verified implementations before the system runs in production. However, this type of work cannot be applied to existing implementations. And another method to verify the correctness of existing systems is to check the safety properties using distributed snapshots during runtime. So this approach can be applied to existing implementations. However, since this requires the checker node to remotely retrieve the protocol states, this can lead to extra communication overhead, affecting the performance. And more critically, if a node crashes, the checker node may be unable to retrieve the remote state, preventing it from continuing the check process. So in our project, Ellsberg, we proposed a new method to verify the correctness of existing distributed system implementations at runtime, but in a local way. The overall architecture of Ellsberg is as the picture. So here, in each node, there is a local Ellsberg instance running with the system process to check whether the system process is running correctly. However, unlike the distributed snapshots, the checker in Ellsberg will not communicate with any other nodes, and thus it will not insert the extra communication costs or affected by the failures of other nodes. And the key idea behind Ellsberg's local design lies in the observation that if all processes correctly follow the protocol, then the cluster must satisfy the safety properties. So let's dig into how the Ellsberg works with the system process within one node. The process is as follows. After providing the protocol specification to Ellsberg, Ellsberg keeps monitoring the external behaviors of the system process, that is, the message trees of the system process. Ellsberg then compares these two to decide whether they are consistent, and if not, Ellsberg will raise an alarm that the process execution has deviated from the protocol spec. So here is an example of how a message trace looks like. It records all the messages received and sent by the system process in linearizable order. We call these in and out messages. And now our goal is to feed this into Ellsberg and check whether the trace is valid. So as we know, a correct implementation should first only change its states given an in message or an internal timeout. And second, it only sends out messages allowed by the protocol. So how we will check the message trace? Ellsberg reproduces the execution using the in messages, and it checks whether each out message is valid given the execution. So as shown in the figure, this is the execution reproduced by the message trace, where we apply the in message R1, R2, and R3 in order, resulting in intermediate states S1, S2, and the final state S3. We aim to check, according to the protocol, whether M1 and M2 are allowed to be sent at states S2 and S3. So specifically to reproduce the execution, we collect the in messages from the trace as the transition edges, and we still need the initial state of the system and the transition functions that are how the states will be updated when handling different messages. and these will be derived from the protocol spec. So in general, given the message trace, Ellsberg is able to reproduce the execution and check whether the system only sends out valid messages. However, there are still challenges remaining to be solved. So first, in real world, the systems are often composed of multiple threads and resulting concurrent execution. Second, since we target checking the system at runtime, the message trace keeps growing. So here is an example of concurrent execution we observed. So suppose the leader received the two requests R1 and R2 concurrently from different clients. And then it appends them to its log and broadcasts a penalty request to other nodes, trying to commit them. Then it further receives another client request R3. Similarly, it appends the R3 to its log and broadcasts a penalty again. The message trace of this process is shown at this, but here we can observe that the leader processes client requests in the order R2, R1, R3, since R2 appears in the log earlier than R1. However, in the message trace, R1 appears before R2, since this is the order that the nodes receive the message, but not the exact order that the node processes the message, because of the concurrent execution. So therefore, when Ellsberg checks the message, considering the concurrent execution, it cannot just process the message trace in order. For example, in this case, the trace order corresponds to the execution order R1, R2, and then R3, which is not aligned with the real order. And the second challenge is that the trace keeps growing at runtime, and we have to figure out a way to check the incremental part of the trace, instead of checking from start each time, which is not scalable, especially after the system runs for a long time. So to solve the two challenges talked about, we propose two corresponding solutions. First, to handle concurrent execution, Ellsberg will enumerate all possible executions instead of only following the order of the message trace. And second, to handle the growing trace, Ellsberg proposes a way of incremental trace checking. Let's first look into the first solution. So as we said before, the order that's how the system processes the messages may not be the same order that appears in the trace. And thus, the real execution order is unknown to Ellsberg. To solve this, we apply BFS to enumerate the orders of all the in messages, and this should cover all possible executions. So then our goal is to check among all these executions, can Ellsberg find one that for any out message M in the trace, the execution leads to a state S such that the state S can send the message. For example, in this case, we can find a path. We need to find a path such that for both the out message M1 and M2, there exists a state that is allowed to send the message. We start from the message M1 and check this by examining each state in the BFS procedure. And then the question is how we decide whether the message is allowed to be sent at a state. We observe that the out message often informs us about the current state. So given the M1 message in the example, we can infer from it the current term of the system, the order of the request in the log, and even infer that the current node is the leader from the type of this message. We call this process inference. This is a function required in the Ellsberg spec. So this approach not only efficiently checks whether a message can be sent at a state, but also enables us to apply optimizations to prune the BFS exploration. So in the paper, there are more details about how we optimize the explorations. So then, given that the log in the message M1 is R2, R1, Ellsberg finds out that M1 can be inferenced from S5, which is the states after applying the client request R2, R1 in order. Similarly, Ellsberg concludes that the state S6 obtained by applying R3 to S5 can be inferenced from M2. As a result, Ellsberg successfully finds an execution R2, R1, R3 that satisfies the requirement. And more concretely, in this execution, S5 can send M1 and S6 can send M2. Therefore, Ellsberg decides that this trace is valid. Then we move forward to the second challenge, that is, we apply incremental checking to handle the growing trace. We observe that since all the in messages that can lead to the out message M1 must appear before M1, as the trace grows over time, the prefixes of the paths that eventually pass the checking are actually the same. This is because the paths leading to the previous sent out messages are not affected by the future incoming messages. So our basic idea is that each time we see an out message M, we find all paths starting from the S start and leading to the send out message M. We call this state S end. And then we set the S end as the new S start for the next round of exploration. So taking the raft example just mentioned, in the first step, when we encounter the first message sent, which is M1 here, we need to find all the paths that can reach M1. So after enumerating all paths, we find only the path R2 to R1 satisfies the requirement for sending M1. We move on to the second step, where the S2 will be set as the starting state for the next round of exploration. And moreover, we have to remove the input messages used in this round, namely R1 and R2, from the available transitions for the next round. After completing all these steps, the search for the message M1 in this round finishes. Next, we continue reading the message trees until we encounter the second out message M2 here, starting a new round of exploration for the paths leading to M2. We attempt to incorporate R3 into the path and find that its final state exactly satisfies M2. Therefore, Ellsberg concludes that this message sequence is correct. So here, if we modify the M2 to include an unseen request R4 instead of R3 here, Ellsberg will find that it cannot find any path satisfying the sending of M2. And it will conclude that this message trace is incorrect. So in summary, the essence of Ellsberg's local checking is to determine whether such an execution path exists. It requires first to collect the in-out message trace from implementation incrementally, and then given the initial state and transition functions defined by the protocol and the inference function defined by the user, Ellsberg applies incremental checking and is able to enumerate all possible paths and thus find out whether there is a matched one. We implemented Ellsberg in Go and evaluated it using 3 open source DPIs, SAD, Zookeeper, and Redis Raft, where we reproduce and successfully detect 10 bugs in total. Here, we present the performance of Ellsberg while deploying in production, since we aim to run Ellsberg together with the system process at runtime. So this is the latency number of the running system, which is SAD here, without and with Ellsberg. We run SAD with 120 client threads, which results in SAD's peak throughput. We can see that deploying Ellsberg in production ensures very low cost. This is because Ellsberg only uses 2 cores and there is no network resources required. And the overhead relies on generating and transmitting the trace. We also test the Ellsberg's throughput of processing the messages in the trace compared with the throughput of SAD generating the trace. This number matters since if Ellsberg has lower throughput, it cannot keep up with the implementation in production. However, from the testing results, we can see that for SAD, Ellsberg has at least 2 times higher throughput, which means Ellsberg can keep up with the system. There are more details in the paper, including that how we optimize the BFS exploration to make Ellsberg's performance scalable and extra contents related to the evaluation. So in conclusion, we propose RPRC, Runtime Protocol Refinement Checking, a new way to check the correctness of existing distributed protocol implementations. And RPRC shows a local solution that doesn't require coordination or communication, and thus make it an efficient way to check correctness of deployed DPI at runtime. We have the code, and we will be happy to help if you are interested in applying this approach to a deployment. So thank you so much for your attention, and I'm happy to take any question.